Okay, so let's start the video with this remark. You may remember that we ended our previous analysis video with the taxicab metric, which we defined on any Euclidean space Rn, where n can be any positive integer. Now next in this remark, the author says that the taxicab metric has many applications, and one of those applications is in the theory of error correcting codes. So let's see how the connection can be made. Say you have a binary string like this where there are only zeros and ones, 1 0 0 1 0. Now you can think of this string as this 5 tuple in R5 because 1 and 0 are after all real numbers. With this understanding, you can then apply the taxicab metric to calculate the distance between two such binary strings. Say between this binary string and this another one, 1 0 1 0 1. So what does the taxicab metric do? It takes the corresponding coordinates. It takes their numerical difference and then adds them up. That is the taxicab metric distance value. So you can note that here 1 0 1 0 are the same. The first two bits of these strings are the same. So the corresponding differences will be 0. So they are not going to contribute anything to the sum. However, the last 3 bits are different. Here you have 0, here you have 1. 1 0 0 1. So each one of them contributes a 1 to the sum, and that's how you get this value 3. Now how can you interpret this 3? Okay, fine, so it is some value. How can you interpret this 3 as the distance between these two binary strings? So what I am trying to say is that what significance does 3 have? You see, 3 in a sense tells us how different the two binary strings are from each other. In the sense precisely that these two are different in precisely 3 places. In the first 2 places they are not different, but in the remaining 3 places they are different there everywhere. Okay, so then what do we do with this, and what is the relation between this and error correcting codes? You see, you already know that whenever you, where do we use this type of things? We use these things in devices. Say your computer. A computer does not really understand anything other than these ones and zeros, where 1 represents the state of a very tiny switch, something. I don't really know these things exactly, so I'm just simply saying vaguely whatever I know. So there are some extremely tiny switches in a computer. So these switches can either be switched on or off. So when a switch is in switched on state, that represents 1, and when it is switched off, that represents 0. So what the error correcting codes do is that they correct errors. What errors? See, sometimes what happens is that there is noise, some outside disturbance. You may hear traffic every now and then in these videos, so that type of thing. So it is creating disturbance for us. Sometimes a computer may be disturbed. In exactly what way, I also don't know. So that accidentally, say a switch which is off, which represents this 0, gets switched on. So you now have 1 here. Alright. So this is an error. The error correcting codes have to repair these things, the corrupted information. Now the role that the taxicab metric plays here is this. First of all, whenever you want to put something on your computer, it has to be transformed into these binary strings, right, using some kind of scheme something. Say you get these 2 binary strings. 1 0. For the sake of simplicity, let me just consider 3 bits, 1 0 1. Now what happens is that some outside disturbance comes and switches on this switch, so that it gets transformed into this. Then you cannot, whatever then has to be done to correct this, there would be problem, because this is not corrupted but this is corrupted. It's difficult to distinguish between the two because now they are same, right? Why did this happen? It happened because originally the two strings were very much like each other. They only differed in exactly one place, these last bits. Or in other words, the distance between them in the taxicab metric was very small, 1. So in that sense, they are very close to each other. And that created the possibility of one entire string being transformed into another one accidentally. It increases the chance. The closer these two strings are in the taxicab metric, the higher the chance is that one will get transformed into the adjacent, I should not say adjacent, but one which is near. So in order to minimize this, obviously the error correcting code has to encode things in a way that will keep these strings as far away from one another as possible, say in this metric. Okay, so that is why we need this thing. And it also helps us detect that something has gone wrong with this string. If you have a group of people who are dressed alike and they look also more or less like the same person, if you keep them very close together and look at them from distance, then it's difficult to tell them apart. Instead, if you keep them quite spaced apart, then you can easily detect if something went wrong with one of them, say. Okay, so in that sense, we need this in error correcting code. You see, it's clear, I am obvious that there are many things behind this. So this is just one indication that in this way these things can be applied. Okay, it's not just that you incorporate this distance into some such code, some such program and the job is done. It's not really that simple. But anyway, so this was the remark. And after that there are other examples of metric spaces. So next let's see them. So this is the next metric space. We have already defined two metrics on Rn, any Rn, little l1 and little l2. Little l1 is the taxicab metric and little l2 is actually the first one that we define, that is the Euclidean metric. And here is another such, little l infinity. This is called sup norm metric. Sup stands for supremum. Okay, so let's see the definition. N of course again is a positive integer, a positive natural number, and Rn is our Rn. So dl infinity of course has this as its domain and this as its range. So the dl infinity distance between this n tuple and this n tuple of real numbers is the supremum of this set. What is this set? In this set we consider the numerical difference between the corresponding coordinates of these two tuples, and we take the supremum. So you can see that actually this is a finite set. So instead of supremum you can also write maximum if you want. However, it has an infinite version also. That is why in general we write supremum. We need not worry about those infinite versions or whatever they may mean. So you just treat it as maximum. For example, if we go back to the example that we have been taking, when we discussed the L1 metric and L infinity metric, we calculated the distances between these 2 points in those metrics. So let's calculate this L infinity distance also. So you would have to consider these two numerical differences between 1 and 4 and between 6 and 2. So this one is 3 and this one is 4. So the maximum between them is 4. Okay, so 4 is the distance between these 2 points in the subnorm metric. And the fact that this is actually a metric space, we will prove in exercise 12.1.9. Now, just like there is a relationship between L1 and L2 metric, which is given by some inequalities, there are relationships between, similar inequalities are there between L infinity and L2 metric. Let's see what they are. Okay, so the relationships are given by these inequalities. For any two elements x and y in Rn, 1 divided by square root of n times the dl2 distance between them is less than or equal to the dl infinity distance between those 2 points, which in turn is less than or equal to the dl2 distance between these 2 points. And these inequalities that you are seeing and the one that you saw before, in the previous video, these inequalities ultimately are going to show that on Rn, it does not really matter which metric we choose, because you will see what it all means, that these 3 metrics on Rn essentially give us the same metric space. Same means I should not perhaps say same, but similar metric spaces. This is not a technical term, okay? We do not really have anything called similar metric spaces, but they are in a sense same. Okay, but anyway, so after that there is this remark which one cannot fail to notice, because we are using similar notations to denote these metrics L1, L2, L infinity, and these 3 metrics are special cases of the more general LP metric, where P can be any real number from this interval. So we have already seen the cases P equal to 1, 2 and infinity, okay, but there are other P's also can be considered, although we are not going to discuss these things in this book. So let's see what comes next. Next we have this example 11, and here the metric has a name. It's called a discrete metric. I say a discrete metric because it's not a single metric exactly. Depending on which set it is defined, it changes. So the definition is this. Oh, but before that, let us consider X to be any set. Any set, okay. We are no longer considering necessarily Rn or anything else. This can be any set. This may in fact be a finite set as well. Now the distance function that we define on this x, we are calling it d suffix disc. Disc stands for discrete. D disc is a map from x times x into same stuff as usual, but this is the definition, and the definition tells us that between any 2 points x and y, the distance is measured like this. X and y of course are coming from x, both of them. If they are same, then the distance is defined to be 0, which is what we expect. But if they are different, then the distance is constantly 1. Now it turns out that yes, this also is a metric. It satisfies all those 4 conditions that a metric has to satisfy. So that turns any set x into a metric space, and that is called a discrete metric space. And this we will prove in this exercise. In this metric space, you can see that all the distinct points are equally far apart. The distance between any 2 distinct points is 1. Okay, it sounds strange, but it is what it is. And also it tells us that any set whatsoever can be turned into a metric space. On any set there is at least one metric, which is this discrete metric. And do you remember that when introducing the Euclidean space Rn and when defining the Euclidean metric dl2, I said that besides these metrics there is another metric also, discrete metric. So here you can in fact consider Rn. So on that Rn also you have this discrete metric. Next, this informal example which involves geodesics. This term geodesics you will find in differential geometry and you will find in Einstein's general theory of relativity. It is informal because the author is going to say something here which we won't really prove. So the set that we consider here is the sphere in 3 dimensions. So it is the set of those points x, y, z in R3 such that x square plus y square plus z square equal to 1. This sphere of radius 1, okay, in 3D, this thing. It's the surface, of course. On this surface, say you take 2 points. So you can think of the surface of the earth as this thing. Say you consider these 2 points. Okay, so this is, let me write the coordinates here. So this point has coordinates x, y, z, and this is this. Now the distance that we measure between these 2 points now is not the straight line distance that we usually measure when we think of distance in 3-dimensional space. Instead, here the distance between these 2 points is considered to be the length of the shortest path. Oh, I forgot to write. Length of the shortest path in x or on x that starts at this and ends at this point. Not just any path. If we are allowed to choose any path, obviously that length will be the length of the straight line segment in 3D joining these 2 points. Not that. Those paths that are trapped on the surface itself. There may be many paths like this. It's like choosing 2 locations on earth and going from one location to another, say by flight, okay, on an airplane. Now there may be many routes. One of those routes will have the shortest length. That length is considered to be the distance between these 2 points. Now it turns out it's a fact that that length will be the length of an arc which lies on the great circle passing through those 2 points. What is a great circle? You see, you have the sphere. If you cut the sphere using a plane, say a gigantic, we are thinking of the earth, no. So we have a gigantic blade which can cut the earth in 2 parts. So if the cut passes through the center of the earth, then you can understand without being too mathematical, you can just simply understand that the earth will be separated into 2 equal halves. And that cut will create a circle, that is a great circle. Why do I say a great circle? Because you can have infinitely many such cuts, all pass through the center. And these great circles are largest possible circles that lie on the surface of the sphere. As opposed to these cuts, if it cuts here somewhere, then also you get a circle, so those are small circles. It's a fact of the geometry of sphere that this length of shortest path lies on a great circle. You may think it sounds a little counterintuitive that we should have a small circle, but that's not the case actually. So some such great circle passes through these 2 points and say, then we will actually get 2 paths. No, one of them is this and the other one is this. The one which is of smaller length will have that length which will be the distance between these 2 points. In this metric, it is also a metric, but we want to prove this. The fact that this thing happens needs the calculus of variations for its proof, which we don't really know at this stage, and we won't worry about that. However, the author also says that in spite of all these difficulties, you can in fact consider the triangle inequality for this D and can actually prove it. So for triangle inequality, you have to take another point. Say you don't know this fact that the arc that whose length will be this distance lies on a great circle. You just simply use the definition that it's the length of the shortest path in X joining the 2 points. Just using this definition, can we prove triangle inequality? The author says yes, and actually it's quite easy. Let's see, okay. Let's see that figure. So that is our sphere. On them, for the sake of simplicity, I am just giving these points some simple names, x, y and z. We won't even need their coordinates for this. Say the shortest path joining x and y is this path. There may be more than one such path. What do we know? Okay, we know almost nothing. We just know this definition. One of them is this. Its length is small, although it looks really very wavy, but you can understand that I am not actually assuming any particular type of path. That's why I have drawn this type of very ugly looking path. So this is a shortest path between x and y. This is a shortest path between x and z, and this one is a shortest path between y and z. So what does the triangle inequality say? It says that this is less than or equal to dx comma y plus dy comma z. All right. Now you think of this side. What is this? This is the length of, let me give this path some name, okay. So let me call this P1, P2, P3. These paths may actually intersect one another. Although we haven't shown that here, they may intersect one another, but that does not have any effect on our argument. So this is the length of P1. This and this second one is the length of P2. And this is the length of P3. Now instead of going from x to z along P3, we can also go along this path where we first follow P1 to reach y, and then from there we follow P2 to reach z. That is also this which I can write like this, say P1 union P2. This is possibly another different path to go from x to z. Now by the definition of this distance, this is the a path of shortest length, and this is any path. So the length of this path will be greater than or equal to the length of this path, and the length of this path is this, whereas the length of this path is this right hand side. That's it. And finally we have this another informal example. and this one is called shortest path, in a sense that you will understand now. This is also informal because we are just simply going to discuss about something and we won't really go too deep into this. Say X is the set of all computers connected to the internet right now. Some of the computers may not be connected, but X is the set of those that are connected right now. And for any X and Y in X, that means this X and Y are two computers connected to the internet. D of X comma Y, let it be the smallest number of connections it would take for a packet to travel from computer X to computer Y. If there is another computer between them, say X and Y are not directly connected to each other, but their connection is through this intermediate computer. Okay, so Y may be some computer where you have something which you want information about, okay, and you connect your computer X to the internet. That means you switch on the internet, or it's already connected. So you type something there, okay, say on your Google search. Then the connection is made via Z. So then the distance between X and Y is 2, the minimum number of connections that would take you from X to Y, or in the language of this network or whatever it is, the minimum number of connections it would take for a packet to travel from X to Y. So you can clearly see that in this situation what we are really considering is a graph from graph theory. So on a graph, whatever you know as distance between two vertices, it is that same distance. Okay, and it turns out that the set of all computers, or in general the set of vertices in a graph, becomes a metric space with respect to this metric. Okay, so it's just the last example of metric spaces for now. So now that we have gathered some examples of metric spaces, now we can go back to the point where we can start mathematics again. Okay, so that we will do in the next video. But that will be all for tonight. See you tomorrow with a new upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.